Welcome to this scientific lecture on Hooke's law, one of the most fundamental principles in physics that describes how springs and elastic materials behave when forces are applied to them. Our story begins in the 17th century with the brilliant English scientist Robert Hooke. In 1678, Hooke published his groundbreaking observations about elastic behavior. Hooke conducted systematic experiments by hanging various masses from springs. He would attach a mass to the bottom of a spring, allow it to come to rest, and carefully measure how much the spring stretched. You might ask, what exactly was Hooke trying to discover? He wanted to understand the fundamental relationship between the force applied to an elastic material and how much that material deforms. Let me describe the experimental setup in detail. Imagine a spring hanging vertically from a fixed support at the top. First, we measure the natural length of the spring when no mass is attached. This is our reference point, the equilibrium position with no external force. Step 1. We attach a known mass to the bottom of the spring. The spring stretches downward due to the weight of the mass. We wait until the system reaches equilibrium, where the spring is no longer moving. At equilibrium, two forces balance perfectly. The downward weight force, which equals mass times gravitational acceleration, is exactly balanced by the upward restoring force from the spring. The difference between the new length and the natural length is called the extension, which we denote as x. Step 2. We carefully measure the extension. This requires precision. Hooke likely used a ruler or measuring stick positioned next to the spring. Step 3. We repeat this process with many different masses. Perhaps we start with 50 grams, then 100 grams, then 150 grams, and so on, recording the extension for each mass. Now here's a crucial point. The force applied to the spring is not just the mass, it's the weight of the mass. Weight is mass times the acceleration due to gravity. F equals m times g, where F is force in newtons, m is mass in kilograms, and g is the acceleration due to gravity, approximately 9.8 meters per second squared. Let's do a quick calculation. If we hang a 200-gram mass, what force does it apply? First, convert grams to kilograms. 200 grams equals 0.2 kilograms. The force is 0.2 times 9.8, which equals 1.96 newtons, so a 200-gram mass applies approximately 2 newtons of force. After conducting the experiment with multiple masses, Hooke and later experimenters would organize their data into a table. Let me show you what typical data might look like. Here's example data. Notice that as we double the mass from 50 to 100 grams, the force doubles from 0.49 to 0.98 newtons, and the extension also doubles from 2.5 to 5 centimeters. This pattern continues consistently. You might wonder, why is this pattern so significant? Because it suggests a direct proportionality. When one quantity doubles, the other doubles. When one triples, the other triples. This is the hallmark of a linear relationship. The next crucial step is to create a graph. We plot force on the vertical axis and extension on the horizontal axis. Each data point represents one measurement. When we plot these points, something remarkable emerges. The data points fall almost perfectly on a straight line passing through the origin. This straight line relationship is the key discovery. The fact that the line passes through the origin makes sense. When there's no force, there's no extension. Zero force means zero deformation. What does this straight line tell us mathematically? A straight line through the origin has the equation y equals k times x, where k is the slope. In our case, force equals k times extension. This brings us to Hooke's law. Based on the experimental observation of a linear relationship, we can write a mathematical law. F equals k times x. Force is proportional to extension. The constant of proportionality k is called the spring constant, or stiffness constant. What exactly is this spring constant? It's a measure of how stiff the spring is. A large K means a stiff spring that resists deformation strongly. A small k means a soft, easily stretched spring. The units of K are newtons per meter. If K equals 100 newtons per meter, it means you need 100 newtons of force to stretch the spring by 1 meter, or 1 newton to stretch it by 1 centimeter. Let's calculate K from our example data. We can use any point on our line. Let's use the point where force is 1.96 newtons and extension is 0.1 meters or 10 centimeters. K equals F divided by X, which is 1.96 divided by 0.1, giving us 19.6 newtons per meter. This spring constant tells us this particular spring is moderately stiff. Let me give you an analogy to help understand Hooke's law. Think of the spring constant like the personality of different people when you ask them for favors. A stiff spring with a large K is like a stubborn person. You need to apply a lot of persuasion or force to get even a small change in their behavior or extension. A soft spring with a small K is like a very agreeable person. Just a little persuasion, a small force, produces a large change in behavior or extension. Here's a critical question. Does Hooke's law work for all amounts of stretching? The answer is no. There's a limit called the elastic limit. If you stretch a spring too far, you enter the plastic region where the material is permanently deformed. In the elastic region, shown in green, Hooke's law works perfectly. The spring returns to its original length when you remove the force. But beyond the elastic limit, the spring is permanently damaged. Why does the spring eventually fail? At the atomic level, springs are made of atoms bonded together. When you stretch moderately, the bonds stretch like tiny springs themselves, but stretch too far and bonds break. Atoms slip past each other, and the structure is permanently altered. There's another way to write Hooke's law that emphasizes an important concept. When you stretch a spring, it exerts a restoring force, trying to return to its natural length. F spring equals negative K times X. The negative sign is crucial. It indicates that the force exerted by the spring is in the opposite direction to the displacement. If you pull the spring to the right, it pulls back to the left. This negative sign embodies the very nature of elasticity. Elastic materials resist deformation. They always try to restore themselves to their equilibrium position. Let's work through a practical problem. Suppose you have a spring with a spring constant of 50 newtons per meter. You hang a mass of 500 grams from it. What is the extension? Step 1. Calculate the force. The mass is 500 grams, which is 0.5 kilograms. The weight is mass times g. F equals 0.5 times 9.8, which equals 4.9 newtons. Step 2. Use Hooke's law. We know F equals K times X, so X equals F divided by K. X equals 4.9 divided by 50, which is 0.098 meters, or approximately 9.8 centimeters. Here's another problem. A spring extends by 15 centimeters when a 300-gram mass is attached. What is the spring constant? We're given mass equals 0.3 kilograms and extension equals 0.15 meters. The force is 0.3 times 9.8, which equals 2.94 newtons. The spring constant is F divided by X, which is 2.94 divided by 0.15, giving us 19.6 newtons per meter. When you stretch a spring, you do work against the restoring force. This work is stored as elastic potential energy in the spring. The elastic potential energy equals 1/2 times K times X squared. Notice this is proportional to the square of the extension, not just the extension it's. Why is there a factor of 1/2? Because the force increases linearly as you stretch. At the start, the force is nearly 0. At the end, it's K times X. The average force is 1/2 K times X, so the work done is average force times distance. Let's calculate the energy stored in our previous example, where we stretched a spring with K equals 50 newtons per meter by 0.098 meters. E equals 1/2 times 50 times 0.098 squared, which gives us approximately 0.24 joules. This energy would be released if we let the mass bounce back up. Hooke's law is not just an academic curiosity. It has profound practical applications throughout science and engineering. First, vehicle suspension systems use springs to absorb shocks from the road. Engineers carefully choose spring constants to balance comfort and handling. Second, spring scales use Hooke's law directly. The amount of spring stretches tells you the weight of an object. Third, in earthquake-resistant buildings, engineers design structures with controlled flexibility. The building sways like a spring during an earthquake, absorbing energy without collapsing. Fourth, At the molecular level, the bonds between atoms behave approximately like tiny springs. This helps us understand vibrations in molecules, heat capacity, and even sound propagation. Hooke's law applies to many elastic materials beyond coiled metal springs. Rubber bands, elastic cords, even the compression of gases for small changes follows similar principles. The general principle is that stress is proportional to strain. Stress is force per unit area, strain is fractional deformation. For many materials in the elastic region, stress equals a constant times strain. This constant of proportionality is called the elastic modulus, also known as Young's modulus for tension and compression. Different materials have vastly different elastic moduli. Let's discuss the limitations. Hooke's law assumes several things that aren't always true in real situations. Assumption 1. Deformations must be small compared to the original dimensions. For large deformations, even in the elastic region, nonlinear effects appear. Assumption 2. The material must remain in its elastic region. Beyond the elastic limit, permanent deformation occurs, and Hooke's law fails completely. Assumption 3. We assume static or very slow loading. At high speeds, dynamic effects, vibrations, and wave propagation become important. Let's appreciate the genius of Robert Hooke's discovery. In the 17th century, without modern measuring instruments or calculators, Hooke recognized a simple mathematical pattern in nature. He found order and predictability in something as seemingly chaotic as the stretching of materials. This was a profound insight that nature obeys mathematical laws. Hooke's law unified many seemingly different phenomena, from the bending of beams to the compression of gases, under one simple proportional relationship. Let me summarize the essential concepts we've covered in this lecture. Hooke's law states that force equals K times extension. The spring constant K characterizes the stiffness of the elastic material. The law was discovered experimentally by observing that force versus extension graphs produce straight lines through the origin for many materials. The law is valid only within the elastic limit. Beyond this limit, permanent deformation occurs. When a spring is stretched or compressed, elastic potential energy equal to 1/2 kx squared is stored. The principle applies across scales, from engineered springs and machines to atomic bonds and molecules, making it one of the most versatile laws in physics.